how do we go about finding the line that has the smallest sum of squared residuals? Well, I'm going to kind of just hop right to it as to what that best line is. The least squares regression line is the line that has the smallest sum of squared residuals. So this is the best line. The equation of the least squares regression line is given by y hat. We're using y hat because this is going to give us predicted y values equals b sub 1 times x plus b sub 0. So b sub 1 is representing the slope, whereas in algebra, we use m for slope. We don't do that in statistics. And then b sub 0 is representing the y-intercept. So again, different notation, just so you understand that. Now, how do we go about finding the slope and the y-intercept? Well, the slope is going to equal r times s sub y over s sub x, where r is the correlation coefficient, s sub y is the standard deviation of the y variable, and s sub x is the standard deviation of the x variable. So that's the slope of the least squares regression line. Now, just to kind of explain where that kind of comes from, I'll just draw a little picture here. So if I have data that's doing something like this, then in order to find the slope, like we did with the golf data, in order to find the slope, when I found 2 points, we know we do y sub 2 minus y sub 1 over x sub 2 minus x sub 1. Well, what we want to do here is not just find the slope between 2 points, we want to find sort of the average slope. So that's where this comes in. So the standard deviation of y gives us sort of the average rise, and the standard deviation of x gives us sort of the average run. So we're doing the average rise over the average run, which is the change in y over the change in x on average, and that is our slope. But the trouble is standard deviation is always positive. So we would always end up with a positive slope, even whenever we have a negative relationship. So we multiply by the correlation coefficient, and that's going to give the appropriate sign to the slope. So if we have a positive slope, r will be positive. If we have a negative slope, r will be negative, and that will make the slope negative. And it also factors in the strength of the linear relationship. So it's a perfect linear relationship. R would either be 1 or negative 1. And so R wouldn't really change the slope at all. It would just be the standard deviation of y over the standard deviation of x. But if we have a looser relationship for that, R is going to factor into that as well. The y-intercept, the way this is going to work is we're going to use the average of y, or the mean of y, so y bar, minus the slope times the mean of x, x bar. So the y-intercept equals y bar minus the slope times x bar. Now where that comes from is this. So if I were to take all of the x coordinates and find the mean, that x bar would be somewhere here in the middle, like this. If I were to take all the y coordinates and find the mean of those, y bar would be somewhere in the middle, like this. So if I have that point right there, that point would be the point x bar, y bar. Our line that best fits the data will go through that point, the average point. So we're finding kind of the average slope, and we're finding the average point. The line's going to go through that point and have the average slope. Now, if the line's going through that point, then if we know y equals the slope times x plus the y-intercept, well, if the line's going through this point, then that means x is x bar, and that means y is y bar. So if I just subtract this b sub 1 times x bar from both sides, I get y bar minus b sub 1 times x bar equals b sub 0, the y-intercept. That's where this formula comes from. So the y-intercept equals the mean of the y coordinates minus the slope times the mean of the x coordinates. So that's the logic behind it. Let's do an example. As always, we're going to do one example by hand, and then I'm going to show you how to use technology, and we will use technology from then on to find our regression line. So for the data to the right, and so I've just picked an example from the textbook. Again, I picked it just because it's going to be relatively easy. By hand, draw a scatter diagram treating x as the explanatory variable and y as the response variable. So I've provided a grid here for us to make our scatter diagram. So we have the point 30, which would be here. We have the point 52, which would be about there. We have 7,3, which would be about there. 9,6, about there. And 11,9 would be about there. So there's my by hand scatter plot. Do those points look linear? Well, they look fairly linear to me. It's certainly not perfect. Certainly not perfect, but it's somewhat linear. Part B, select 2 points from the scatter diagram and find the equation of the line containing the points selected. So this is going to be like what I did back here for the golf data. I picked 2 points and I found the equation of the line that goes through it. So that's what we're going to do in part B, and we're going to graph that in part C. In part D, we're going to by hand determine the least squares regression line, and we're going to graph that as well. Then we're going to compute the sum of squared residuals, both for the line we found in part B, and we're going to do that for the line we found in part D, the least squares regression line, and we're going to comment on the fit of the 2 lines. So the point's going to be that the least squares regression line is the better fit. So what I'm going to do, I'm going to just pick 2 points, but I want to pick good points that's going to be somewhat a decent model. So I think I'm going to pick this point and this point, okay? So this is going to be my line for part B. So I'm going through the point 5,2, and I'm going through the point 9,6. And so I've selected those 2 points, and I'm going to find the equation of the line that goes through those 2 points. So part B I'm going to do down here. So I need to find the slope. So the slope of those 2 lines, and I'm going to use algebra notation, that's M. That's going to be y2, which is 6, minus y1, which is 2, over x2, which is 9, minus x1, which is 5. So that gives me 4 over 4, which is 1. So this line that I just found has a slope of 1. So now I know the equation of this line is going to be y equals 1x plus something. To figure out what the y-intercept is, I can use either the 0.52 or the 0.96. Doesn't really matter. You'll get the same result either way. I'm going to use 5,2. So if I substitute 5 for x and add the y-intercept, the result should be 2, the y-coordinate. So 2 equals 5 plus the y-intercept, which means the y-intercept is -3. So the equation of that line right there is y equals 1x minus 3. Now, by the way, that looks like a line that's a pretty good fit, but it's still not going to be the best. Part C, graph the line found in part B. Well, I've done that. So that's going through that point and that point. So now D, I want to find the least squares regression line by hand. Now I'm going to kind of cheat a little bit for this. I'm going to do it by hand, but I'm going to let the calculator find all of the stuff that I need. So I'm going to need to know the correlation coefficient. I'm going to need to know the standard deviation of the y variable, the standard deviation of the x variable, the mean of the y variable, and the mean of the x variable. I'm going to need to know all of those things in order to be able to find the least squares regression line. And I'm not going to calculate those by hand. I'm going to let the calculator do that for me. So I'm going to go to Stat and Edit. And I have some stuff in the calculator. I'm going to keep that. That's the bare data in list 1 and list 2. I'm going to keep that there. I'm going to put this data in list 3 and list 4. So 3, 5, 7, 9, 11, and 0, 2, 3, 6, 9. So I have the X's in list 3 and the Y's in list 4. Back to the home screen. I'm going to go to Stat and Calc. And since I have two variables, I'm going to have it calculate two variable statistics. I have my X's in list 3, I have my Y's in list 4, and I'm going to calculate. So the calculator is telling me that X bar equals 7. X bar equals 7, so I'm going to write that down. The standard deviation of X equals 3.162278 if I round to 6 places. Y bar equals 4. S sub y equals 3.535534 if I round to 6 places. Now, this doesn't give me the correlation coefficient, but I'm going to go find that. I can go to Stat and Calc, and I can do linear regression. My X's are in list 3, my Y's are in list 4. So if I calculate the correlation coefficients there at the bottom, it is 0.9838. That's going to be 70 if I round to 6 places. Now I'm carrying that out several places, 5 or 6 places, because if you round that, then you're going to get rounding error. We're still going to get rounding error, but it's not going to be as significant as if I were to round like to 3 places. Then I'm going to get some significant rounding error, at least potentially. So I've got the information I need. I need to find the slope and the y-intercept so that I can get my regression line. So the slope, B1, is going to equal, I'm using my formula up here, the correlation coefficient times the standard deviation of y over the standard deviation of x. So my correlation coefficient is 0.983870, so that's R, times the standard deviation of y, which is 3.535534, divided by the standard deviation of x, which is 3.162278. So if I bring in my calculator, 0.983870 times 3.535534 divided by 3.162278, that is 1.100000012. So if I round again to 6 places, that's going to be all zeros after the 1. So this is approximately 1.100000 if I go out to 6 places. So really about 1.1. The y-intercept is equal to y bar minus the slope times x bar. So y bar, that is 4, minus the slope, 1.100000 times x bar, which is 7. So 4 minus 1.100000, I'm not going to write that, times 7, that is about negative 3.7. So my least squares regression line is going to be the equation y equals, I'm just going to say 1.1 times x minus 3.7. There's really no point in writing all of those zeros in this regression line. So this is the answer to part D. Usually when I write a regression line, I don't use y hat as the variable here, but your textbook will. So it will write y hat equals 1.1 times x minus 3.7 instead of just y, because that's really giving us a predicted y value, not an observed y value. That's the distinction. So we're supposed to graph the least squares regression line. So I'm going to use a different color for that. Since I don't have a nice, neat slope or a nice, neat y-intercept, I'm going to graph this by finding a couple of points. So what if I were to plug, say, 4 in this equation? Well, 1.1 times 4 minus 3.7, that would be, whoops, I hit minus instead of times here. That should be times. So that should be 0.7. So 4.7 would be around there. And then if I were to plug in, say, like 10, 1.1 times 10 minus 3.7, that is 7.3. So 10, 7.3 would be maybe around in there. I plotted those 2 points, and if I connect them, that would be my regression line. So there is a little bit of difference between my regression line and the line that I drew first. So now we're supposed to find the sum of the squared residuals for both the line we found in part B and then also for the line we found in part D. So let's do that. So I'm going to have to do that on a separate sheet of paper. So I'm doing part F here, where I am finding the sum of the squared residuals. So again, I'm going to write down my equation, y equals 1x minus 3. And I'm going to make a quick table here. So we had 3, 5, 7, 9, 11 as the actual x values, 0, 2, 3, 6, 9 as the observed y values. So the first thing I'm going to do to find the sum of the squared residuals is I'm going to find all of the predicted y values. So if I were to substitute 3 in this equation, y would equal 1 times 3, which is 3, minus 3, which is 0. If I substitute 5 in this equation, 1 times 5 is 5, minus 3 is 2. If I substitute 7, 1 times 7 is 7, minus 3 is 4. 9, 1 times 9 is 9, minus 3 is 6. And 11, 1 times 11 is 11, minus 3 is 8. So I get these predicted y values. Now again, my model's doing a pretty good job because look, my predicted y value was the same as the y value for this point, and this point. It was only different for 2 different points. The next thing I'm going to do is I'm going to calculate the residuals. So I'm going to take the observed y value minus the predicted y values. So for this first point, y was 0, the predicted y value is 0, 0 minus 0 is 0, so that's the residual. 2 minus 2 is 0, that's the residual. 3 minus 4, that's negative 1. 6 minus 6 is 0. 9 minus 8 is positive 1. Notice, by the way, if I were to add up all the residuals, I get a sum of 0. That will always happen. So I'm going to square all of these residuals. 0 squared is 0. 0 squared is 0. Negative 1 squared is 1. 0 squared is 0. 1 squared is 1. So if I add that up, I get a total of 2. That is the sum of the squared residuals. And that is the sum of the squared residuals for my equation, y equals 1x minus 3. Now I'm going to do the same thing for the regression equation. And so our regression equation was y hat equals 1.1 times x minus 3.7. So I'm going to do the same kind of thing. I'm just going to begin by rewriting my x's and y's. I'm going to find y hat. So if I substitute 3 in this equation, I'm going to get 1.1 times 3, which would be 3.3 incidentally, minus 3.7, that is negative 0.4. If I substitute 5 in, 1.1 times 5 is 5.5, minus 3.7 is going to be 1.8. Plug in 7. 1.1 times 7 minus 3.7 is 4. 1.1 times 9 minus 3.7 is 6.2. And last but not least, 1.1 times 11 minus 3.7, that is 8.4. So again, look at this. Up here, 3 of our 5 points, our predicted y value was exactly the same as the observed y value. There were only 2 differences. For all of these, we were off. But when I find the residuals, so I'm going to take the observed minus the predicted. So I'm going to take 0 minus negative 0.4. 0 minus negative 0.4 is going to be positive 0.4. 2 minus 1.8 is 0.2. 3 minus 4, negative 1. 6 minus 6.2, negative 0.2. And 9 minus 8.4 will be 0.6. If we were to add up those residuals, it would add to 0. It always does. So if I find the squared residuals, well, 0.4 squared will be 0.16. 0.2 squared will be 0.04. Negative 1 squared will be positive 1. Negative 0.2 squared will be positive 0.04. And 0.6 squared will be 0.36. So if I add that up, 0.16 plus 0.04 plus 1 plus 0.04 plus 0.36, that equals 1.6. That is our sum of squared residuals. Notice that the sum of squared residuals for the least squares regression line is 1.6, whereas the sum of squared residuals for the other line was 2. And so this is smaller than this. It would be impossible to get anything smaller than 1.6 from the sum of squared residuals. So if we draw any other line through these points, if we draw any other line, it's going to give us a larger sum of squared residuals than 1.6. This is the minimum. So comment on the fit of the line found in part B versus the least squares regression line found in part D. Well, the line found in part B has a higher sum of squared residuals than the least squares regression line did. So that means the line found in part B is not as good of a fit. It's not a horrible fit, but it's not as good as the least squares regression line. I do want to show you something about the calculator. When I did stat and calc and I did linear regression in order to find the correlation coefficient, look what it gives me. So I got the correlation coefficient, and that's all I wrote down because we were doing it by hand. But look right here. A equals 1.1, B equals negative 3.7. That was our slope and our y-intercept. So the calculator, when I go and find the correlation coefficient, it actually also finds the least squares regression equation for me. So now the calculator calls the slope A and it calls the y-intercept B. So the slope is 1.1 and the y-intercept is negative 3.7. So really, I knew the answer to that problem when I found the correlation coefficient. I knew what the least squares regression line was going to be. Now, normally that's not going to come out nice and neat like 1.1 and negative 3.7. You're going to get this trail of decimals that you're going to have to round. But in this case, it worked out nicely.